Hello, class. Um, this is team group number 2. The topic is quantum computing. This is our presentation for CSC 607. Alaki Peoples, Gerardo Castro, and Gregory Casamento. Next slide, please. So, what is quantum computing? Quantum computing, we're going to talk about these 4 items to discuss the essentials of quantum computing, which what is a qubit, what is decoherence, what is superposition, and what is entanglement. Next slide. Qubit, quantum bits. So traditionally, computers work with bits. It's either 0 or 1, 2 states only. Quantum computers, on the other hand, work with qubits, which exist in superposition, which is a state of being in 2 states at the same time. It's a little bit of 0, a little bit of 1, and just as like spinning a coin in the air. So, to give you a better idea, a traditional computer performs one calculation at a time because of bits, but a quantum computer can hold these multiple states simultaneously, so you can actually perform many calculations at once. Finally, qubits are atoms, ions, photons, or electrons. Next slide, please. Entanglement. This is another concept uh, that we would like to discuss, and that is that quantum computers will harness the power of atoms and molecules to perform memory and processing tasks. Quantum computers have the potential to perform certain calculations significantly faster than any silicon-based computer. Through entanglement, scientists can actually measure a value in a qubit when it is found in superposition. That measurement must be made indirectly so that you don't disturb or bump the subatomic particles, because that would cause the value to actually change. So you get these inaccurate values. So in quantum physics, if you apply an outside force to 2 atoms, it can cause them to become entangled, and the second atom can take on the properties of the first atom. So if left alone, an atom will spin in all directions, and the instant it is disturbed, it chooses one spin or one value. And at the same time, the second entangled atom will choose an opposite spin or value. This allows scientists to know the value of qubits without necessarily looking at them. Next slide. Decoherence. This is an interesting topic because it is where the challenge comes in. Decoherence is a source of error. As I was mentioning before, when uh, the qubits alone, when you leave them by themselves, even in the most physical stable condition, they will eventually lose their informational value and entanglement because of the interaction with the environment, just by a change of temperature or a single molecule of air that interferes can actually disturb the particles. So to compensate for this error, quantum error correction is used. This means that more qubits are actually needed, as well as the amount of processing for error correction. But once these technical challenges are resolved, quantum computers are very valuable in solving mathematical problems that traditional computers cannot actually solve in a reasonable period of time. Next slide. So here we're going to talk about forecasts on disruption. Uh, there are three encryption standards officially released to prepare for the future of quantum attacks. We're going to talk about what is NIST, how does the quantum computing approach encryption, and these different types of mechanisms and algorithms. Uh, they are the standards. Next slide. So, what is NIST? National Institute of Standards and Technology is a U.S. federal agency that develops standards and guidelines for science, technology, and cybersecurity. NIST led an international effort to evaluate and standardize cryptographic algorithms that can resist attacks from quantum computers. Next slide. So, how does QC approach encryption? How do quantum computing approach encryption? Basically exploits superposition, interference, and entanglement to run specialized algorithms that solve certain mathematical problems much faster than a classical computer. So, as we mentioned before, a classical computer, a bit can be a 0 or 1. A qubit can be both at the same time. This is called superposition. As for the role of interference, quantum algorithms manipulate the amplitudes of states so that incorrect answers interfere destructively and correct answers interfere constructively and become more likely. Next slide. Okay, so here we want to talk about the standards officially released. One of them is Module Lattice Base Key Encapsulation Mechanism. So it's formerly known as Crystal Kyber. It was standardized as FIPS 203, and it's used to establish uh, key establishment and encryption. It allows two parties to securely exchange a shared secret over an insecure network. And based on the difficulty of solving mathematical problems involving module lattices, this is intended to replace current public key encryption such as RSA and elliptic curve Diffie-Hellman, which could be broken by just having enough power of the quantum computers. Next slide, please. So the next one is module lattice-based digital signature for algorithm. This one's known as a crystals dilithium, also standardized as FBPS 204, and it's used for digital signatures. And it provides authentication, integrity, and non-repudiation. It also relies on hard problems involving module lattices. It is intended to replace current digital signatures algorithms such as RSA and ECDSA in a post-quantum environment. Next slide. Okay, lastly, we have the other uh, uh, release over here, the stateless hash-based digital signature algorithm. This one is formerly known as SPHINCS plus Sphinx, standardized as FIPS 205. And this is another algorithm for digital signatures, based entirely on cryptographic hash functions rather than lattice mathematics. Stateless means users do not have to maintain state information between signatures, simplifying implementation. It also provides an alternative in case lattice-based approaches are later found vulnerable. Produces larger signatures and is generally slower than MLDSA, but offers strong security based on well understood hash functions. Next slide. Okay, we want to add a brief sidebar. So, what the heck is module lattice? Module lattice. So, a lattice problem is a hard math problem involving a grid of points in many dimensions. So, in cryptography, the challenge is usually to find a very short vector or a specific hidden point in that high dimensional grid. This is easy to describe but extremely hard to solve when the lattice has hundreds of thousands of dimensions. The difficulty is what makes lattice-based encryption useful for post-quantum security. Next slide. And yes, to where we want to get to, prediction for the future of cryptography. So post-quantum cryptography will replace RSA and ECC. Hybrid systems combining classical and quantum-resistant algorithms will be common during the transition. AES-256 and other symmetric algorithms are expected to remain secure. Some new algorithms may eventually be replaced as cryptanalysis advances. Cryptanalysis advances. So it's estimated by the 2040, that's my estimate, that RSA and ECC may be viewed as legacy technologies, much like DES is today. Overall, quantum computing is expected to drive a major evolution in cryptography rather than cause a collapse of digital security. Next slide. Okay, I'd like to summarize this section. So, quantum computing takes a unique approach to encryption that leaves a large number of classical algorithms vulnerable to attack. This could have a drastic effect on security as quantum computers become more powerful and prevalent in the future. Together, all of these standards represent the first officially approved post quantum computing cryptographic algorithms, providing protection against both classical and future quantum computers attacks. Next slide. Okay, now we want to talk about quantum enigma machine. If this would be the actual ultimate solution to encryption and secrecy. And according to research, the laws of quantum physics certify the secrecy. The, it works through a communication protocol where a shared key between two parties. The third party will not be able to tamper or obtain the key, because the moment that it disturbs the molecules and the particles, then the key is lost. So there's the way this is all done is through quantum data locking. That's how private communication is based on. The information is encoded by a single photon quantum state. Next slide. So how do we know that secure encryption is actually possible? Well, we have a mathematician, Claude Shannon. He proved in 1949 that information theoretic secure encryption, that means with unlimited computing power, encryption is actually possible if the encryption key is used only once, is random, and is at least as long as the message itself. But through the findings of the quantum data locking technology, an actual short secret key can be used and can encrypt as much as the longer message if it's done through the quantum system. So no longer necessarily need the same size key as a message. Next slide. Here I would like to demonstrate an experiment that shows quantum data locking, how it works. And in this experiment, the UV light was used, and it was sent through a crystal to produce photon pairs. As you can see in the dashboard, we have Alice, Bob, and Eve. Alice is the sender and encodes and locks the information. Bob is the receiver, and Eve is the one tampering over the information. So basically this works by encoding a 6-bit of information to a single photon while encrypting that information with less than 6-bit key. And as the experiment applied Reed-Solomon protocol and transmitted 420 packets of 63 photons with a successful rate of 99.5%. Next slide. Lastly, I would like to talk about Urmila Mahadeb. This is a graduate student that would not graduate from school. She spent at least 8 years only just in graduate school because she came out with this question that was haunting her and curious about it, and that is, How do you know whether a quantum computer has actually done anything that's quantum at all? So she found a way, and this really solves those accuracy issues that were mentioned. So she want to find a verification. How can we verify that the thing is actually working? So she has come up with an interactive protocol by which users with no quantum powers of their own can nevertheless employ cryptography to put a harness on a quantum computer and drive it wherever they want, with certainty that the quantum computer is following their orders. Okay, with this we conclude our slides. The next will be our references. Thank you.